In this example, find a VO in the network using nodal analysis. VO is over here. Because nodal analysis is a systematic way to perform circuit analysis, it doesn't really matter what you are looking for eventually. So you follow the standard process, just pay attention to the last step when you draw a conclusion. Alright, let's do that. So in loop analysis, the first step is always to define reference node, right? And label nodal voltages. So some students had a question about like, where do I select the reference node? Technically speaking, it doesn't really matter. You will get the same answer no matter which node that you select as a reference node. But there are generally two things to consider when you select reference node. Because you want a limited number of equations to have, right? So you want to find a node that has more branches connected to it. That might be good. The second rule to follow is by looking at what you are looking for from the problem or what's given from the problem. So in this problem, VO is defined as the voltage between this node and this node. So this is why for this problem I'm going to select this node as my reference node. The second step is we haven't labeled all the nodal voltages yet, so we'll label the nodal voltages. So there's one node that's called VO here. So this node will have a nodal voltage of VO. If we make full use of what's given in the problem, we know that this node is higher than node VO by 12. So this
VO
node
plus
will
12?
Yes. So that will be VO plus 12. And there is another node over here that we don't know, right? So we'll call that node V1. So now we define all the nodes. So this is a reference node, VO, V1, and a VO plus 12. We'll get everything. So the next thing to do is to write the nodal equation, right? At which node do we want to write the nodal equations? So we cannot write a nodal equation about the node that has a connection with a voltage source, right? So looks like we cannot write it from here. I cannot write it from here. So I can write a nodal voltage at a node V1, or I can write a nodal voltage at a node at the reference node, right?
Wait, Professor, I have a question before. How come can you explain a little bit more why we couldn't write the equations on V0 and V0 plus 12? What
Sure.
are we?
So if we write a node, assume that we want to write a nodal equation over here, we are going to write the nodal equation by using Ohm's law for the currents, right? So we are going to count the current leaving this node as up to 0. So this branch, no problem. So it will be VO minus V1 divided by 2. This branch, no problem. And how about this branch? How do we write the current going through this branch? So there's no resistor. We are not going to have Ohm's law to help us to write the nodal, the current equation, right? So this is why we cannot write a nodal equation here.
Okay, thank you. That makes sense.
Mm. So at the node V1, we have V1 minus this is 0 divided by 1. And when we label it a nodal voltage, it means that this node and the reference have a potential difference of a V1. The current in this branch, that is V1 minus VO divided by 2K. And the current in this branch, that is V1 minus VO plus 12 divided by 1K. So now we got all the three branches connected to this node that is equal to 0. So this is the first equation about node V1. The second node will be the reference node, right? At the reference node, we count all the current. You can count all the current leaving the node, or you can count all the current goes in, it goes into the node. It doesn't matter. So if we do all the current goes into the node adds up to 0, so that will be V1 minus 0 divided by 1. And the second is VO divided by 2. And the third branch is over here, that is minus 4, that is equal to 0. So we count all the current goes into the reference node adds up to 0. So this is how we get the two equations. The step 3 is to solve the equation. So I'm probably not going to solve them. I would like to give more time for me to answer more questions.
There's one on the chat.
So then after we solve the equations in this problem, because VO is one of the nodal voltages that we use, so you just last step just draw the conclusion. That is straightforward. Can you go over example that have to do with loop analysis? Yes. So loop analysis 3.108, right? So we're going to look at that problem. Any further questions on this problem? So you don't need me to solve that, right? Because like we already...
No. Professor, do we always go back to the reference node to write the equation?
The reference node, right? So
yeah.
For the reference node, there are 3 branches connected to the reference node, right? So one branch to the reference node, one branch connected to the reference node, and one branch connected to the reference node. And these 2 dots, this is one node. Although we have 2 dots over here, but this is one node because there's no element in between. So that's something that you need to pay attention to write the equation about the reference node.
Okay, thank you.
3.108. So let's look at this problem. Using mesh analysis to find a VO in the circuit. So what's special about this problem? This current source is special, and it's shared between 2 different meshes, right? And on top of that, there's a dependent source. So when we have the problem like this, it means that this is the last type of problem, but at the same time, we have if we only have the shared current sources, that is, I think, the third case, right? So it's a combination between the third case and the last case where we have dependent sources. So it means that we have these 2 different cases we need to deal with. So whenever we have a shared current source like that, it means that we can either use the super mesh method or the general loop method. Let me just talk about both of the 2 different methods so that you get a chance to review both of the 2 ways to solve this problem. No matter which method that you use, the first step is always to define mesh or loop current, right? So normally I would just say define a loop current. Mesh current is a special loop current. Define the loop currents. Say this is my current I1, method 1, super mesh method. So in super mesh method, we define the mesh current like what we do normally. So we have 3 different meshes. So we have it means that we have 3 mesh currents. So let's call this one I2, and call this one I3. Now we need to write the equation. But between 1 and 3, because they shared this branch, and this current has to be equal to 6 milliamp, so it means that it will give us a constraint I1 minus I3 is equal to 6. Step 2, write the loop equations. So the first equation is a constraint between 1 and 3, so that is I1 minus I3 is equal to 6. The second equation, we know that all the loop equations are written by using KVL, right? For the second loop, it's the same. We write a KVL equation. For the second loop, you can do it element by element. Say this is 12K times I2 plus 8 times I2 minus I3 plus 4 times I2 minus 1. So that is one way to write it, right? So let me put it down there. You can, for the second equation, you can write element by element. You have 12 times I2 plus this is 8 times I2 minus I3 plus this is 4 times I2 minus I1 is equal to 0. So this is one way to write this equation. You can also write it in the other way. Say I'm going to group them directly. The coefficient for I2, that is a summation of all these resistance. So that is so 8 plus 12 plus 4, and a minus is the rest, right? The rest is the coefficient for I1, that is the shared resistance, which is 4. So minus 4 times I1. And shared with I3, that is 8. So minus 8 I3. And there's no voltage drop. There's no voltage source in the mesh. So this is how we write the second equation. So these 2 are identical if you look at it. So we look at the coefficient for I2, we have a 12 and a 8 and a 4. So we have 12, 8, 4. The coefficient for I1 is here, so it's a negative 4. That's negative 4 here. The coefficient for I3, which is a negative 8, we have negative 8 over here. So either way to write this equation should be fine. So, but we only needed 1 because these 2, the way to write them is exactly the same. So right now we only have 2 equations.
Professor, I have a question.
Yes.
So on the first equation, could you also write I3 minus I1? Or what's the reason why is I1 minus I3 equal to 6?
So basically the current in this branch, if you look at this loop, the current I1 is in the same direction as this 6 milliamp current source, but I3 is in the reverse direction.
I got it. Okay. Yeah, thank you.
Not a problem.
Professor?
Yes.
For that first equation, why didn't you write equals 6 Vx?
I don't have 6Vx. This is 6, not a 6Vx.
Oh, okay. Yeah, because on the image it says 6 Vx. Oh, you're looking at the 6 milliamps. My bad.
Yeah, the current source. We are looking at the current source. That is a voltage source.
So we just ignore that?
No, we haven't got that yet. You cannot ignore anything from a circuit diagram. So if we look at the mesh 3, because they have a shared source over there, it doesn't allow us to write a KVL equation. If we write a KVL equation, this is not a problem, so that's a 6Vx, right? But we want to know the voltage drop on this current source.
Excuse me. I have a question. When you write your current for the I1, how come you don't write I1 by 12 kilo ohms?
We are not using KVL to write the first equation, because we cannot write a KVL equation for the first loop.
The second one, the 12 plus 8 plus 4, how come it's not minus 4 I1 plus 12 times I1?
12 times I1. Why do you have 12 times I1?
Well, that's what I'm asking, because isn't it within the current I1?
That's current I2. That was that equation.
This is I2. This
The
is
other
I1.
side. Oh, okay. Sorry.
So this equation is about the loop I2.
Okay.
Yeah. Do you get the idea that we cannot write the KVL equation on here, I1 and I3?
Because they don't overlap.
No, that's because we have the current source. Because this current source, we cannot write a KVL equation about this loop, because we won't know the voltage drop on this current source, right?
Okay.
Oh, so because of that current source, we can't write an equation individually for I1 or I3.
Exactly. So we write the voltage by using Ohm's law, because the current source, it only tells us the current. We don't know the resistance. We cannot calculate the voltage drop. That's why. So it also implies we cannot write a KVL equation for I3. So it means that we short of one equation at least, right?
Professor.
Yeah.
We short of, if we have 3 unknowns, I1, I2, I3, but we only got 2 equations.
So we have to use super mesh right here and take out the 6 milliamp element.
Yes. So you assume this is not there, and you will have you will see another mesh, and this mesh is called a super mesh. So let's draw that. So we'll draw a super mesh.
And this is what you were talking about earlier, right? Basically saying that mesh analysis is basically just loop analysis. Same thing.
Yeah, because the mesh is a special loop. So that is my super mesh. So if we write the KVL equation about this super mesh, so we will have a 6Vx. The second voltage drop is the drop on this 12K resistor. So we're going to write that in terms of the loop current, because we are looking for the loop current. So that is the 12 times I1. There's only one loop current going through that. So that is 12 times I1. And the voltage drop on this 4K resistor, that is 4 times the current following this direction. So we have I1 minus I2. The voltage drop on this 8K resistor, by using Ohm's law, that is 8 times the current going through that resistor. The current going through that resistor following the direction that we are defining, so that is I3 minus I2. So we count everything, that should be equal to 0, right? So now we have 3 equations, but look, by the third equation we introduce a new variable, Vx. just because that's the dependent source. It means that we have 4 unknowns right now, but we only got 3 equations. So we need an additional equation. This additional equation comes from the controlling variable. So we need to find the controlling variable. So we're going to write the controlling variable Vx in terms of the loop current that we defined. In this case, that's a mesh currents, right?
You can use IQ.
What is IQ?
Like IQ equals 4 over
Yeah,
Vx.
it's here. So
What
Vx
is
is over here, right? So we're going to use the mesh current defined I1, I2, I3 to write a Vx. So Vx
Or
is voltage
I2
drop.
minus I1.
Yeah, voltage drop from here to here, and the current going through that from the top to the bottom, that is I2 minus I1, right? So we will write a Vx that is equal to 4 times I2 minus I1. That is how we got the 4 equations with the 4 unknowns. And then you can solve them, and then towards the end give the conclusion. Step 4 will be solve the equations. After you solve the equations, you will be able to find I1, I2, I3, and Vx. So what we are looking for toward the end is VO. Don't forget that. So step 5, conclusion, is to find a VO. How do we find a VO? VO is the voltage drop on here, so that is I1 times 12. So remember, VO is equal to 12 times I1. So that is how we solve the problem, by using super mesh method. So the second method, let's call it the general loop method. So since we know that whenever we have a shared current source like that, we won't be able to write the 3 mesh equations, because these 2 meshes only give us 1 equation. So in the general loop method, we define the current differently. I will not define my current I3 like that. I will define my I3 like this. This is the red is my current I3. So let's change our color then. So now these are the 3 loop currents that are defined. So the first step and the second step, that's the same. Define the loop current and write loop equations. So if we define the loop current like this, current I1 will be equal to 6 in this case, because there is only 1 loop current going through this branch. And the second equation will be KVL equation about this loop 2. So let's write that equation. So we have, so let me copy this. The coefficient for I2, that will be the same, because that is the same resistance, right? But the shared resistance between I2 and I1, that is negative 4 times I1, because I1 is in the different direction as I2. The shared between I2 and I3, now you have 2 elements. So that is 4, and at the same time they are in the reverse direction. Reverse direction here and reverse direction over there. So this is why it will be minus 8 plus 4 times I3. So if you are not familiar with the way like this to write the equation, I would recommend you to do it slowly, element by element. So if I do element by element, I will have the voltage drop on the first element, which is 12 times I2. So I will write it 12 times I2. The voltage drop on this 8K resistor, that is plus 8K times the voltage drop, which is I2 minus I3. The voltage drop on this 4K resistor, that is 4 times I2. So here you need to pay attention. There are 3 loop current going through this element. So we have minus I1 minus I3. So this is how we write the second equation. So you can either do this or do this. I don't matter which method that you use, but make sure that you do it correctly. I'm just going to delete one, so because this is just one equation. And the third equation, if we write the third equation, will be the KVL equation about this loop. So we have so we count the voltage drop one by one. So the first voltage drop is 6 Vx. The second voltage drop is 12 times I1 plus I3. And the voltage drop on this resistor, that is 4 times I1 plus I3 minus I2. And the voltage drop on this 8K resistor, that is 8 times I3 minus I2. So that is how we get the third equation. And we notice that we have a new variable now. We have Vx. The next step is about the control variable. Because we define the loop current differently, so the controlling variable equation might also be different. Vx is equal to 4 times the current flows through this element, that is I2 minus I1 minus I3. So it is 4 times I2 minus I1 minus I3. So that's how we find the fourth equation. After that, you can do the same thing. You solve the equation, then draw the conclusion. So that's how we solve this problem by using these two different methods. So this is a very good example. So this example basically practices everything, almost everything that we did for the for loop analysis. You have a dependent source, so this tells you how to handle the dependent source. At the same time, you have a shared current source, shared between the two meshes, and you know how to do that. You have two different ways to address that. So this is a good example to practice. So any other problem that you want me to look into?
Professor, so for this problem,
Go ahead.
for this problem, the super mesh is easier, right?
I think the two are the same.
Professor, but
Why
will
you
not,
said,
will not be the same, right? Isn't it 12 times A1 plus 8 I3?
Which one?
For V naught, for the conclusion, V naught will be 12 times I1 plus I3.
Oh yeah, you're right. In the general loop method, so when you write the conclusion, so this is no longer 12 I1. So over here, there is a 12 times I1 plus I3 because you have two loop current going through that. So let me put it down here.
So we went over nodal analysis, mesh analysis, and this is basically loop analysis. Is there another similar type of problem that we might see on the exam?
Yeah, review that midterm review video that tells you like all type of problem will be on the exam. I think we went over that on Monday, so we pointed out like how to watch the video.
Professor,
Uh-huh.
are we gonna have to do delta Y transformations?
Yeah, that is required.
I had a quick question regarding the midterm review
Yeah.
video that you posted. So I was confused a little bit on the last thing that you wrote on it. It says identify and use two analysis techniques to solve various applications. So when you mean two analysis techniques, you mean like node analysis and loop analysis, or are there like any other like techniques you wanted us to use?
Loop analysis and node analysis, they are systematic ways to solve problems. So these two are fundamental. So after we learn these two, I'm not going to ask you to use like knowledge learned from chapter 2 to do the calculation problem.
Yeah, but does it have to be the node and loop analysis to solve the problem?
Yeah.
Is that why? Okay.
Yeah. So it'll be either nodal or loop or both. So just pay attention to the requirement from the problem.
Okay, thank you.
And Diana want me to look at problem 3.114. So we're gonna find Ix using loop analysis. So what's special about this problem? So we have dependent sources. It means that we have equations about this controlling variable, right? And at the same time, this current source is not shared. So that's good. That means that it's easier to solve. So I will define my first loop current over here, and the second loop current here, and the third loop current there. So the first step, define loop currents. So I define loop currents like that. And the second step, to write loop equations, right? For the first loop, look at here, because there is a current source, the current going through this branch has to be 2 milliamp. So it implies that I1 is equal to 2 milliamp. And the current in this branch has to be Ix. So it tells us I2 is equal to Ix. And in this branch, it's not special. So we need to write a KVL equation about this mesh, right? So the KVL equation, we count the voltage drop of all the elements in this mesh. and eventually it will be equal to 0. And the voltage drop on this 1 kilo ohm resistor, that is 1 times I3 minus I1. And the voltage drop on this voltage source, that is Vx. So we introduced one new variable, right? And the voltage drop on this 1K resistor, that is 1 times I3 minus I2. That's it. We got all the three elements. So the next, because we introduced a new variable, means that we need new equations which are about these controlling variables. And we have two controlling variables, Ix and Vx. Ix is over here. What is Ix in terms of the mesh currents?
I3 minus I1.
Yes, Ix that is equal to I3 minus I1. And how about another controlling variable, Vx?
Vx equals actually, never mind.
Vx is here.
It equals 2I2 minus I1.
Yeah, perfect. We find that from Ohm's law, right? So the resistance is 2, and the current going through this branch, that is the algebraic summation of these two. And I2 is in the same direction as the current that we needed for that branch. So this is I2 minus I1.
Professor, so for these loops, will we start with KVL first, always?
Can you repeat your question?
For the loops, will we start using KVL to find our equations? Start with KVL first, not KCL?
So remember, nodal analysis is about nodes. So when we talk about nodes, that's where you use KCL. That's where you write a KCL equation. So in loop analysis, we use loop current. We talk about the loops. That's why for any loop that you can write a KVL equation, you count the voltage drop in the loop. All right. Anything else that you want me to talk about? We have another 15 minutes.
Professor, do you mind reviewing the example of delta to Y transformation?
Oh yeah.
In 2?
Which question?
Just the example. I wanted to verify that I understood the diagram in the book.
Okay.
I'll tell you the figure right now.
I can look at
It's
the
figure 2.34 in chapter 2.
I think in this chapter. So let's look at the examples. So this is one example, right?
The delta Y transformation.
So over here there is a delta network.
Because it's not like explicitly in parallel or in series?
Yeah, look, these are three resistors are connected between these three nodes. So here is the same. So 1, 2, 3. So this is delta. And in this problem, I think you also have a delta Y transformation. Let me open the notes that we did before, and I can plan on that. This is the one example that we did before, right? So to simplify the resistor network, we first labeled all these nodes, then we try to find a connection between node A and B. To find a branch connected between node A and B, I need to go through this node C. So this is why I draw the node C over here. Then I try to find a connection between C and B. So I'm trying to look for the connection between C and B. There is one branch over here that is connected between C and B through the two resistors in series. So that's how we put the first branch over here. And we don't have any other branches directly connected between C and B. So it has to go through a new node. So we define the node D. If we define this node D, this is also node D, right? Because this is the same node. This is our node E. So we put them and we find the connection between C, D, C, E. Then we find out, okay, we have a delta network over here. So there are three nodes, C, D, E. So this is three resistors connected between these three nodes. Over here, we cannot use the simplification of resistors in parallel and in series to simplify this. So we need to convert these three resistors in this delta network to be another three resistors in Y-shaped network. So we take the portion out and replace that portion by a Y. This is inverted Y. And the way to calculate RA, that is the multiplication of the resistors connected to this node. So in this case, that is node C. So the multiplication of 12 and 18 divided by the total of the three in this delta shape network, 12, 18, and 6. So that is how we find IA, RA, RB. To find RB and RC, the way to find RB and RC is the same as how we find RA. After you have this new network, and then you can use the resistors in parallel and in series to simplify the network. So RB and 4 in series, RC and 9 in series, and these two branches are in parallel, then in series with RA, then these two giant branches are in parallel, then in series with this 24. So that is how we find the final answer. Anything else?
Oh, no. Thank you, Professor.
You're welcome. All right, any other questions?
Yeah, can we go over chapter 3, 111?
In this problem, we're going to find a Vx in the circuit. So this problem didn't ask you which method to use. So you have freedom to pick like whether you want to use a loop or node analysis. We have about 7 minutes. Let's still try to go over two different methods to solve this problem. And you can select this node as reference node. If I select this node as reference node, then I will have this node have a node voltage of Vx. So if I do that, I will see this node have a node which is Vx. It doesn't really matter. So in this problem, I don't see like a great advantage of defining this node as reference node or any other nodes. What will be the node here? I don't know. What will be the node here? I don't know either. So I will give it a new name. Say like I assume this node will be my node V1. And if I define this node as V1, I will know this node because of this 2 Vx is given. The node voltage for the top node over there, that will be V1 plus 2 Vx. Did I define everything? Yes. The second step is try the nodal equation. The nodal equation is the KCL equation about the node that you are interested in. So can I write a nodal equation here?
No.
Because it's connected to a voltage source, right? How about here?
Yes, because it has resistors.
Can you?
No.
No,
because
it's
it's
same.
a voltage source here, right? So it means that we cannot write it here, we cannot write it over there. And it looks like we have to do it here. And you can write one equation about here. And since we defined two unknowns, Vx, and also there's a new node of V1, so it means that we probably need a second node to write a nodal equation, right? And we'll probably do it here, the reference node. Yes. And since we already used this dependent variable Vx, so Vx is over here, that's the dependent variable, we already use it. So we don't need to write an additional equation about the controlling variable, because the controlling variable is Vx is equal to Vx. So you have two unknowns, you have two equations, that's how you solve it. Now let's see if you want to use loop analysis to solve this problem. To use loop analysis to solve this problem, you need to define loops. For this problem, it looks a little bit complex to use loop analysis, right? Because there are plenty of meshes. There's one mesh over here, one mesh here, one mesh here, and one mesh over there. There are 4 different meshes. So we'll define the first loop current like that. The second loop will be, let's say it's here. So let's call it a loop current I2. And the third loop, let's define it here. Let's call this I3. And the fourth one will be here. Let's call it I4. And the next step is to write the mesh equation. The first mesh equation, which is very straightforward, right? The current is I1 is equal to 10 milliamp. That's good. So we already get one unknown, I1. For the second mesh, it's straightforward. You have 3 resistors. So the coefficient for I2, that is 2, 4, 2. And the coefficient for I1, that is -2, the coefficient for I3, -4, the coefficient for I4, -2. So it seems pretty straightforward to write the second equation. And the third equation is very similar to the second equation, right? Have 3 resistors, and all these 3 are shared. And the last equation, we just write a KVL equation. The voltage drop, this is 2Vx, and another voltage drop, which is 4 times I4 minus I3. The voltage drop on this 2K resistor, that is a 2 times I4 minus I2. Now this is how you get these 4 equations. Then you can solve these 4 equations, and you get I1, I2, I3, I4. After you get that, you can find this voltage Vx by using Ohm's law. Vx is equal to this 4 kilo ohm times I3 minus I2. So this is how you solve the problem using loop analysis. So we went over this problem by using both nodal and loop analysis.